In this video, we will be doing a one-sample right-tailed z-test exercise. So what I'd like you to do in this exercise is work this yourself. You've seen a couple of examples of this already, so really you should be able to do this one on your own. So I'm going to ask you several times to pause and provide your own information as we go through this. A study was performed to test if workers in a steel mill had job-related stress. A random sample of 29 casting workers were measured and found to have a mean post-work heart rate of 78.3 beats per minute. Assuming that the mean resting heart rate of all adults are distributed normally with mean 72 beats per minute and standard deviation 11.2 beats per minute. At the significance level of 5%, is there enough evidence to conclude that these workers have a higher resting heart rate than the general population? So first we need to note that we have the right kind of test. This is a one-sample right-tailed z-test because we are testing for a greater mean in a single sample than hypothesized mean. Notice the whole thing is about means. And notice we're testing for a greater mean because it says higher resting heart rate. That indicates that it's right-tailed test. The distribution of individuals is normal, so the distribution of sample means is also normal, and the population standard deviation is known. So what I'd like you to do now is go ahead and from the words that you see here, work out what the numbers in there stand for. Write the symbols for them, figure out what those numbers basically are, and also state the null and alternative hypothesis. Go ahead and press pause, come back when you're ready. Well, so far we have the sample size is n equals 29. The standard deviation of the x's, the individuals, is 11.2. X bar, which is the sample mean, is 78.3. And the alpha value we're using is 5%, which is 0.05. The null hypothesis, H naught, is that mu equals 72. And the alternative is that mu is greater than 72. Now, I would like you to work out what the test statistic and the standard error of the mean, the sigma of the x bars, are before going on to the next slide. Press pause now. Well, the standard error of the mean is another name for that is the sigma of the x bars. That's the sigma of the x's divided by square root of n. So that's 11.2 divided by the square root of 29. That's about 2.079, etc. So I did that on the calculator right here, and you notice I just stored that as s. That's going to be our standard deviation we're going to be using, which is the standard deviation of the x bars. This way I don't have to type it in again. I can just use it as s. I also took the hypothesized mean of 72 and stored it as m. That one wasn't quite as useful because it's not hard to type in 72, but it's a little harder to type in all these digits for the standard error s. Now, the z-star test statistic is just a z-score for the x bar value, which is just x bar minus mu over the sigma of the x bars. So that's just the 78.3 minus this 72, or 78.3 minus m, divided by this 11.2 over the square root of 29, which we stored as s. So that's just 78.3 minus m in parentheses divided by s, and I stored that as z for my test statistic, which is about 3.029. Now at this point I'd like you to go on and find the critical value and the p-value, and then determine what your conclusion is for this test. Press pause now. Well, we can find the critical value as an inverse norm. It is just the amount of probability, or it's actually an x value, or actually a z value, a z-score, so that the probability to the right, since it's a right-tailed test, is alpha. That means the probability to the left is 1 minus alpha. Well, if there's 5% to the left, there's 95% to the right. So we're just doing an inverse norm of 0.95, comma 01, right here in red. That's 1.644853626, or about 1.64. To make our conclusion, in the critical value method, we would compare the z-star test statistic to this critical value, which is also a z-score, comparing z-score to z-score. We see that 3.029 or 3.03 is greater than 1.64, so we are in the critical region. Z-star is greater than the upper critical value, and so that is enough evidence to reject the null hypothesis in favor of the alternative hypothesis. If we were to use the p-value method, there are two ways we can go at this. We can do p equals normal CDF of our z-star that we just did, which I have stored as z. Go to infinity. Well, we can use 10 instead of infinity on a standard normal, and then 0, 1 for our mean and standard deviation for a standard normal. And we get our p-value of 0.00122, etc., or about 0.001. Notice that that is less than 0.05, actually considerably less, and so that is a very low p-value. That means we have a very low probability of making a type 1 error if we reject the null hypothesis, so we're going to go ahead and do that. We are going to reject the null hypothesis in favor of the alternative hypothesis. In fact, there's maybe a little bit easier way to do this one as well. Instead of figuring the z-star test statistic, we could find the p-value directly from the x-bar value. What is a p-value? It is the probability of getting what we got or something more extreme if the null hypothesis is true. So this is a normal distribution, so we go to distribution. Probability is found with the CDF, so it's just normal CDF. We want to start at our our x-bar value, which was 78.3. We want to go up to infinity. Well, we can do mean plus 10 standard deviations. If we use the standard deviation of the x's, that's 11.2. 10 times that is 112. Add 72, that's 184. Oh, let's just say we go up a little more. Let's go up to 200. And this time it's not a standard normal, but a normal of mean 72 and standard deviation, not 11.2, but rather 11.2 divided by the square root of the sample size, which is 29. In fact, I could just enter it just like that, and this will return a p-value. This is the probability of getting an x-bar value of 78.3 or higher. And voila, that is the p-value that we're looking for. So this method is put in this part down here with the red borders. That's probably the way I would do it. That's an easier way to do that. So let's illustrate that now, both the critical value approach and the p-value approach on a graph. So on the top you see the critical value approach. The critical value was that inverse norm that we did from a standard normal to get a z-score of 1.64. We compare that to the z-score that corresponds to the actual measured sample mean, that was 3.02. We see that the 3.02 clearly puts us well into the red region, so that is strong enough evidence to reject the null hypothesis. The p-value method, it gives us this blue area, which is so small it's almost impossible to see. It's to the right of the z-star test statistic. That area is 0.0012, which is the p-value. Of course, that's much smaller than the red area, which is our alpha value of 0.05. So you really just have to compare these two numbers for the p-value approach. Now, see if you can practice writing down the final conclusion in a little paragraph or a sentence or two here to include your everything that you need for your answer. Press pause when you're and come back when you're ready. So at the top we see the original problem in the red. In the middle we see the conclusion written as you should write it. The mean resting heart rate of casting workers after work is 78.3 beats per minute, which is larger than the average resting heart rate of all adults, 72 beats per minute. With a p-value of 0.0012 from a right-tailed one-sample z-test, this difference is statistically significant at the alpha equals 5% level. In fact, with this low a p-value, there is strong evidence to suggest that casting workers have higher resting heart rate than the general population. Notice that this conclusion includes the type of test, the p-value, the alpha value, and the meaning of the conclusion in the context of the problem. There is some good news on the horizon. Come back for the next video. I think you'll like it.